Keep your hand on your gun. Don't you trust anyone. There's just one kind of man that you can trust. That's a dead man or a gringo like me.
All right, so today we're going to talk about black holes. And we're not going to go too in-depth, just because it's a pretty heavy subject. But we're going to talk about what they are specifically, how they form a little bit, and then how we've detected them so far. So a big part of this is kind of understanding the basics of general relativity. So general relativity itself is kind of, think of space as a trampoline or something like that, where each mass kind of bends the space around it, just like some mass would if it was on part of a trampoline. You'd have like a little dip in that area. So what a black hole is basically a huge mass in this trampoline, to where you don't just have a dip, but you have this big well. You have a huge well into where nothing can get out. Like, say you had, okay, now another part of that. Say you had toy cars on this trampoline, and you had a slow one and then a faster one, and you had the fastest one that there was. So the slow one, you would basically let it go near this black hole, and it would get sucked in almost immediately. Its speed did not matter in getting it into that black hole. And then you have a faster one, and it goes the same distance away from that black hole, but it would go into it, but a lot slower. Like, it would circle around a little bit. And then lastly, say you have the fastest car that there is. And what it does is it goes near that spot and bends. So gravity bends space itself. Is what Einstein's saying with general relativity, and how the trampoline example kind of shows that. In that case, you have masses that are, you have such a big mass in this one portion that even if you had that fastest car trying to get out of the black hole, it wouldn't happen. So if you have a black hole, that region doesn't let out any data. So whether it's photons, any mass is definitely not going to get out, except for, I guess Hawking found out that through quantum effects, like quantum tunneling and things like that, then some energy can get out in the form of gamma radiation, I think is what, or gamma rays is what I think he found. And what the outside ring is that you can't see into is called the Schwarzschild radius. So that's the radius at which basically nothing can get out of. So what you see, instead of seeing that huge mass in the middle, is just a black hole where the mass should be. But we've only found a few ways to detect these black holes, and one way is through gravitational lensing. Say when you have a light going near a black hole, then it's going to bend, and that's not because it's, well, I guess it is kind of because it's affected by gravity, but it's more affected by the bend in space-time. So what you'll see, and we've shown this by looking at stars around the sun. Luckily, it was a few years after Einstein had basically theorized that general relativity was a thing, and he saw during a solar eclipse, and a lot of other scientists saw too, that stars that were very close to the sun at that time looked like they'd shifted. And that wasn't because their actual location had shifted, it was because the sun's mass was shifting. This guy's gonna try to kill me. The sun's mass was shifting the light rays that were coming into it, or in near it. And I'll try to show a picture here of what that looks like. And then also, since Hawking found this gamma radiation, or since Hawking found this Hawking radiation that's supposed to be coming off of it, we've had, I think, Fermi satellite that's been looking for this kind of radiation, and I think to no avail yet, but I'm still not sure. So any star that's like 5 times larger than our star should form a black hole in its lifetime. There's a certain sequence of events that goes on when stars lose a lot of their like fuel. They compound down to a density that's so large that it creates a black hole. So I can show you pictures of how these black holes look as they're kind of being found by gravitational lensing. And what it does is it messes with the way that the background stars are near it, and it's kind of crazy. You just got to check it out and take a gander. I'll put a simulation here maybe. And there's a theory that every galaxy has a supermassive black hole in the middle like ours does. But that'd be really crazy if every galaxy had a black hole in the middle. That's just kind of nuts. A supermassive black hole, that is. So actually humans have been able to create black holes, but the ones we've created have been very, very small. And we've done that with the use of particle accelerators at CERN and other... Actually, I don't know. I think maybe mostly CERN, maybe somewhere else too. But yeah, we've created black holes, but the thing is, they evaporate way quicker because they have almost no mass. I know the big ones would take a long time to evaporate because they have like a smaller surface area per mass, where the smaller ones are just have mass and then like a larger surface area for that, so they could evaporate from their... I actually don't know how they evaporate, so I'm not sure. I'm assuming it would be, you know, radially outward by something. Alright, so at that, I think I'm gonna wrap it up. See you next time, star people of all the places on the YouTubes.